Here, Davide Martizzi, and I'm a postdoc at UC Berkeley, and I'm going to talk about some results regarding supernova feedback that I got in collaboration with Claude-André Faucher-Giguère, Elliot Quethert, and Drummond Fielding. And so I want to talk about supernova feedback because we know it's a very relevant element of galaxy formation models. And we are approaching a regime in which we can do simulations that are fully cosmological, but we can zoom in central regions of halos down to a resolution of 10 parsecs. And we want to improve the modeling of supernovae in this regime. And we want to do it with better models compared to what we implemented in the past. So we have to basically rebuild models like this from scratch, I think. And we had this program that was oriented towards actually studying the problem of supernovae explosion from ab initio, basically. So from single supernovae remnant and building up a model for galaxy formation from this. So the typical scales you have to resolve to get the supernova remnant property, like the whole evolution is like having basically 0.1 parsecs to 10 parsecs. And if you want to resolve the whole evolution of the blast wave properly, you also have a requirement on what's the mass resolution you need to have. So if your momentum of the supernova is P final, and P naught is the initial momentum you put in the medium where the supernova explodes, there's this relation between the swept up mass in the ISM, so the mass that basically is swept by the shock, and the mass of the ejecta. And this translates, if you want a jump of a factor 10 in the momentum, some momentum gain, in this sort of mass resolution criterion. And this is obviously something that you can't reproduce in a cosmological simulation. So this means that even if you want to improve the models, you still have to follow the subgrid approach. So we want to improve subgrid approach for supernova feedback. So the model, basically the problem of supernovae explosions have been studied in classic papers in the 80s and the 90s. And these papers were really interesting. They're like a guiding light for implementing blast wave models of supernova feedback. But they were limited by the fact that they were always assuming an homogeneous ISM. There were 1D calculations and the multiple explosion case was not considered. So there have been, in the last year, 2 years probably, several papers on this topic that were basically trying to look at this problem ab initio from, again, in more realistic environments and using 3D simulations. So this is one of the papers, mine and with the other collaborators, but there are also these other two that are very interesting and more. And so now we'll proceed with describing how we want to study this problem. So we have to imagine that the supernova deposits some ejecta mass and some thermal energy and momentum, and the ejecta first freely expands in the ISM, and then as it sweeps the mass of the ISM, that mass, the swept up mass, starts dominating over the budget. So you enter to this energy conserving Savittov-Taylor phase, which basically is not influenced by cooling. So it's basically just this blast wave that propagates without cooling, and there's momentum gain because of the acceleration of material that's swept up by the shock. And then as cooling starts playing a role, it starts playing a role in a very thin shell that forms at just behind the shock. And this changed the dynamics first to a pressure-driven snowplow phase in which most of the push is coming from the shock gas. And in a final phase, you finally have only momentum conserving, so energy is not conserved anymore, and you just conserve momentum. And so there is a characteristic scale that determines whether you're in the first phase or the last phase, which is this cooling radius. Tells you the radius at which the blast wave expanded before cooling. So we did the experiment of simulating isolated supernova remnants in an inhomogeneous ISM, contrary to what had been done in the past. And we set up some initial conditions that were mimicking turbulence. So they were basically clumpy structures all over the volume. And we basically evolved this blast wave seated at the center with a pretty high resolution. It was like 100 times smaller than 1 parsec. So this is typically what happens when you reach the shell formation time. So this is the cooling time when like the remnant starts to cool. And this is the final phase, which you basically have this hotter bubble in the middle, and you get some sort of colder structure here, and the momentum of the blast wave is conserved. So the reason why we want to do this is that then we can measure the actual momentum of the whole remnant and the actual thermal energy within the shock radius. And so depending on the radius, the scale, we can actually say, if I'm at this distance from the blast wave, this is the momentum I should consider for the injection if I were using a subgrid model. And the same for thermal energy. So in blue, you see the result here of the homogeneous medium calculation, and in green, what happens in an inhomogeneous medium. So the result is very similar. There's the Sedov-Taylor phase early on, like that's energy conserving and momentum increases, and this thermal energy is conserved. And then you cool, and you basically your thermal energy drops, and then momentum becomes flat, so you conserve it. And the only thing that changes in the inhomogeneous case is that the cooling radius is twice the size, because you have paths of least resistance that basically make the blast wave propagate further. But you also have clumpy structure that boosts cooling locally. So you also have this sort of drop of the thermal energy that's more dramatic. So, okay, we calibrated this sort of model with an analytical formula that reproduce all these results at different densities and metallicities. And then we decided to test the analytical formula for the injection of energy in a model in which we adopt this as a subgrid. So basically we choose one fixed injection size for the supernovae, and we, depending on whether we resolve the cooling radius or not, we inject the right thermal energy and right momentum. So we first started considering testing the model in a periodic box of 50 parsecs of side, in which we see different supernovae at a different rate, and the goal is to drive turbulence in the box and sort of get a multi-phase structure. And so you see this is after 1.5, 1.4 mega years from the start of the explosions. You start getting this sort of bubbles, hot bubbles, and this colder material, and the structure is very inhomogeneous in a way. So I'll skip this and go to the result. So if you do a calculation which you resolve every single supernova, you get this sort of kinetic energy density, this very wiggly one, the black one, and this thermal energy evolution as a function of time. So this means that you reach a steady state for turbulence and also for the thermal energy content in the box. And if you adopt the subgrid prescription, that's the red line, you sort of resolve the integral, or the kinetic energy in turbulence and the time average thermal energy in the box. So these were like some positive results. They were quite encouraging. And so we decided to sort of port these configuration in a more realistic environment. So we decided still to test everything in a very controlled environment, but we went to a system that is more similar to a galaxy. So it's a stratified medium. So there's an external gravitational field here. There's a gaseous disk, but that has a gas fraction of 10%, and it should be non-self-gravitating. So the resolution here is 2 parsecs, and so we start seeding supernovae one by one in the disk to get a result like this. And so you have initial transition in which cooling basically makes the disk collapse, but then everything is heated up by the supernovae. So you get turbulence in the disk, and you also get these sort of hot bubbles that basically move out very fast. There's a sort of steady state that you develop, and there's also a steady outflow in this particular simulation with this particular configuration. So what we did is to consider how the energy is distributed between turbulence, outflow, and also cooling, because we also have cooling there. So if this is E dot, which is basically the energy rate in each component. So if we inject this black rate here, so it's actually all the energy deposited by supernovae, the red line will be what you lose in cooling. So a lot of energy is actually lost in the disk. So when you see the supernova in the disk in the high density region, so the cooling radius of the supernova is so small that they don't overlap, and so you cannot blow a super bubble in this case. Anyway, if the supernovae explode in a low density region, it's easier to blow a super bubble, and so that's what generates the outflows. So this is actually the energy budget you get for an outflow, the blue line. And actually, only 1% of the energy goes into driving turbulence. So it's a very tiny amount. And so the next thing we've done is to measure mass loading factors. And we did it in two kinds of simulations. So there were the simulations with the fixed supernova rate, in which we just decide to see supernovae randomly, so totally randomly in volume. And in the other case, we use peak driving. So we preferentially select the density peaks. And this actually changes a lot the result, actually. So if you see your supernovae at the density peaks, the density is going to be higher, the cooling will be faster, and the net energy basically injected by the supernova is lower. So you're going to blow less gas out. So this is the mass loading factor. It's a factor 10 to the minus 1 close to the disk, and it depends on the height. And if you basically put supernovae out of the disk, it's going to be basically slightly stronger. So this is an argument to say it really matters where you put the supernovae. And so maybe I'm close to the end, but so these are very idealized simulations. They consider like limited volumes. If you double the volume, there are some effects that influence the results that are due to boundary condition problems. So all of these needs to be ported to a more realistic scenario, which we basically have a non-stratified geometry, something more spherical, a global simulation probably. And so we have to reconfirm these results in a more realistic environment. And so I leave you with the conclusions here. And yeah.
Thank you.
Thank you.
Again, time for a couple of questions.
So we have done similar work. The paper you couldn't mirror actually Lee at all. Okay, so what we found is that if you just divide the gas into cold, warm, and hot, the hot gas is sort of conducive to forming superbubbles.
Yeah.
Where the warm gas in the middle is most damaging in terms of suppressing the bubble formation. Where cold gas doesn't matter that much.
Yeah.
So we found that if you include more physics, for example, if more PE heating, just to evaporate the cold clouds, filling up the wind channels, so speaking, between the cold clouds, then you tend to suppress the bubble formation. In other words, additional microphysics might be important to consider in a simulation.
So you will basically have some cooling radius in this model that depends on the local density at the subgrid scale.
Takes a go first.
Hi. I was wondering if you could comment on how the scale height of your disks evolve. I couldn't really tell. I mean, you seem to see an initial contraction, but do you ever see an expansion? Because I think Steffi Walsh had a paper not too long ago where they have a similar setup, and they do see an overall expansion of the disk over time, and I was just wondering if you see that.
Okay, so what I'm doing here is, so without cooling, this will be at equilibrium, but then I turn on cooling, and so that's why you see this sort of initial, basically like collapse of the disk. Mm-hmm. But then you puff it up again. Yeah.
You puff it up again.
Yeah.
So does it ever equilibrate? Does it ever?
Yeah, it goes to an equilibrium where the scale height is something like 60 parsecs here.
Okay.
But it depends on the surface density of the disk, because this is a particular simulation, but I had other surface densities, and they behave differently.
Okay, thank you.
Yeah.
Davide, It's in a comment in the same line as the previous comments. Have you supernova, before they go supernova, these are massive stars and they're emitting a lot of radiation. And so do you have an idea what would happen if you pre-photo heat the gas with this radiation and then have your supernova explode? Do you think that would change your results?
Yeah, I think that will change something, because in principle you can excavate cavities, right? And so in this model, if you just implement this brute force on top of that effect, this will lead you to having larger cooling radii. Larger cooling radii mean basically that you have a much longer set of Taylor phase, so you inject more energy, and that will be more efficient.
Along the same lines, Rogers and Pittard had a paper in 2013 where they did something similar, but also included radiative heating and winds. And I think they showed something along the lines of 90% of the supernova energy ends up coupling with the warm ISM beyond the initial cloud. Would it be simple to kind of include these additional feedback mechanisms like winds in your model?
I think it will, yeah. It's just that we were trying to do like the minimal model in this series of papers and then like add complexity. Yeah, so.